Hello and welcome to the second video on Gibbs phase rule. So in last video we saw that as we are adding alloying elements, we are changing the phases which we can have in a system, and we saw a rule called Gibbs phase rule which can help us find how many degrees of freedom we have before we cross into another phase boundary. So we saw that the Gibbs phase rule is basically the phases plus degrees of freedom is equals to components plus 2. And one mnemonic to remember this equation is basically pull plus force is equals to cops plus 2. Now let's see what it means to apply this into a phase diagram. But before we do that, we need to understand something else. So in most of the metallurgical processes, we just consider the effect of temperature. That is, we see how temperature affects a phase transformation. And we usually ignore the pressure because most of the processes are occurring at 1 atmospheric pressure. So we are not really changing the pressure. So this is not considered as a variable. And so now we have something called a modified phase rule, wherein we are reducing the number of variables by 1. So you have P plus F is equals to C plus 1. But as we saw in the other video, as we start adding another element into this A, let's call this element B, and we start adding into A, then we need to know what phases will occur at what temperature and at what concentration of B. So this is plotted in something called a phase diagram, wherein now you have another axis which is concentration, and here concentration is denoting the amount of B atoms inside the A. So on this end of the axis you basically have pure A, that is 100% A atoms, and as you move towards the end of this axis you basically have 100% B atoms, that is pure B here. And what you do is map out all the possible phases which you can get for varying concentrations and temperatures, and this is called a phase diagram. Here the regions are basically phases. For example, here you have a single phase wherein you are at A rich site, and as you are moving towards the B, there are more and more B atoms. Similarly, here you have a B rich phase, and then as you are moving towards the A side, you are getting more and more A atoms. In these phases, we denote it by Greek alphabets. For example, this we call it alpha, this we can call it beta, and the liquid phase we denote it by L, right? The spaces in between these phases are called two-phase regions, and you have basically alpha plus beta here, liquid plus beta here, and alpha plus liquid here. So this is sort of like a map which tells us where a phase can exist and where phases have to coexist and where they have to change. Now let's apply the Gibbs phase rule to this hypothetical phase diagram. So let's try to apply it in this single phase region called alpha. In this case, we have two components, A and B in this phase, and you have just one phase in equilibrium here, since only alpha can exist in this region. So basically, if you substitute these values, that is, you have two components and just one phase, you get the degrees of freedom to be 2, and which is true because in this region you can change temperature and composition, and you can still remain in alpha region, right? Similarly, you can apply it to beta, and you see that you can also get 2 degrees of freedom. Now let's apply this degrees of freedom to a special point, which is this. At this point, you have 3 phases in equilibrium, that is, liquid can coexist with alpha and beta at this particular point. And if we try to apply the Gibbs phase rule, we see that we have 2 components and 3 phases now in equilibrium. So the degrees of freedom is 0, basically meaning that for this system with A and B, the 3 phases can only coexist at this particular temperature for this particular concentration. This point is usually called the invariant point, and this reaction where a liquid can give rise to 2 solids is called a eutectic reaction. Now let's apply Gibbs phase rule in this 2-phase region. So from our Gibbs phase rule, we have degrees of freedom coming out to be 1 because we have 2 phases in equilibrium. However, if we see here, we can change temperature and concentration and still remain in this 2-phase region. But the Gibbs phase rule gives us degrees of freedom to be 1, which means that these two are not completely independent. They must be dependent on each other, and we basically can change only one variable independently. So for now, let's remove the concentration and let's choose one particular temperature arbitrarily, right? Which means that at this temperature we have chosen, and now if we try to vary the concentration, what happens is that you are not actually changing the composition of alpha and beta. The composition of alpha and beta are fixed by these endpoints. That is, the alpha anywhere in this region at this temperature will have the composition of this particular point. And similarly, beta will have the composition of this particular point. However, by changing the concentration, what we are changing is the amount of alpha which is present, that is the phase fraction. That is, at this end you have more alpha, while you are going towards this end you have more and more beta. That's the only thing that is concentration is changing, and it's not actually changing the composition of the phases itself. So now if you change the temperature, what happens is that the composition of alpha and beta will get automatically fixed depending on the temperature, and these points will lie along these boundaries. So in truth, as you also see, that what you are changing is one thing at a time. That is, you are changing only temperature and the compositions get fixed. And the change in concentration only results in a change in phase fraction, but not actual change in the composition of the phases. So this is in fact true that we have only 1 degree of freedom. And this was the misconception that I had, because I thought since we are changing concentration and we can also change the temperature, we have 2 degrees of freedom, but Gibbs phase rule tells us only there is 1 degree of freedom. Now let's go to another hypothetical phase diagram where we do not have beta phase. That is, the B atoms do not really like to have any A atoms inside them. So the beta phase or the B phase exists as pure B. That's it. However, still the A atoms can still accommodate some more B atoms. So you have a phase called alpha phase wherein if you are moving towards B, you have more and more B atoms, right? So now the question becomes, can we apply the Gibbs phase rule here? Because this phase, that is the pure B phase, has only 1 component, whereas the alpha phase here has 2 components. Now let's generalize this even more and see when we have P phases and the last phase, the Pth phase, has 1 less component. That is, all the P minus 1 phases have all the components C, and the last phase has C minus 1 components. And we want to see whether we can apply the Gibbs phase rule or do we have to change it. In order to do that, we can again arrive at the Gibbs phase rule by figuring out how many variables we have and how many equations we have. Now it's straightforward to figure out how many variables we have, since for P minus 1 phases you have all the components. The number of phases changes to P minus 1, whereas the number of variables is still same. So P minus 1 times C minus 1 plus 2, which is temperature and pressure, that exists as is. And for the last phase, since you have 1 less component, you get additionally 1 more minus 1. And the number of variables turns out to be this. Now to figure out the number of equations which we have when we have this Pth phase which has 1 less component, we can see that for C components, because they exist in P minus 1 phases, you would have C times P minus 1 minus 1 equations. And for the last phase, since you have only C minus 1 components, you can only get C minus 1 equations. So the number of equations becomes this. So we figured out how many variables we have, and we figured out how many equations we have. And now in order to find out the degrees of freedom, we subtract variables minus equations, and we get the same equation again. So there is no need to change the Gibbs phase rule when you have phases with less components than in the overall system. The Gibbs phase rule still turns out to be P plus F is equals to C plus 2 even in this case. So hopefully the video I made on this Gibbs phase rule is clear, and if you have any doubts or any questions or suggestions, please feel free to reach out to me. Thank you for watching.